Tonight, astronomers have found a star that belongs to the Milky Way, sitting more than 1 million light-years from Earth. The part of our galaxy you can actually see is about 100,000 light-years across. This star is more than 10 times farther out than that. It sits almost halfway to Andromeda, and astronomers still measure it moving under the Milky Way's gravity, not drifting free. So how far away is the edge of the Milky Way really? Every time we think we have measured it, the edge turns out to be farther than we said. The last time a team of astronomers sat down and tried to measure the whole of the Milky Way, the number they came back with carried an uncertainty wider than the entire galaxy most of us grew up picturing. They put the diameter at about 1 9/10 million light-years, give or take 400,000. The bright pinwheel of stars you picture when you hear the words Milky Way is only about 100,000 light-years across. The part of their answer they were unsure of was several times larger than the whole galaxy we thought we lived in. A margin of error that size is not the galaxy being big. It is the measurement admitting that when our finest tools go looking for the far edge of our own home, they cannot agree with themselves to within a distance 8 times the width of everything we can see. This is not a fact that has been nailed down. It is a question still standing open, tonight, while you lie here in the dark. For a long time, I assumed a gap like that was something better telescopes would eventually tidy up, the way a blurred photograph resolves the moment you find the focus. The history of this question runs the other way. Every time we built an instrument sharp enough to pin down the size of the galaxy, it did not confirm the old number and hand back a cleaner version of it. It found a new edge, farther out, that the earlier instrument had been blind to. 100 years ago, the answer sat near 100,000 light-years, and the people writing it into their notebooks felt they had the galaxy more or less measured. Then the answer grew, and grew again. Not once because the Milky Way was getting larger, but because we kept finding another layer of it that had been there the whole time, sitting past the reach of whatever we were looking through. So the question is not how big is the galaxy, as though a single clean figure were stamped on its side, waiting to be read off. When we ask how far away the edge of the Milky Way is, the edge of what do we mean? The galaxy does not have one edge. It has several, folded one inside another like layers you keep peeling back, sitting at wildly different distances, and every one of them is real. Consider what you can see on a clear, dark night, well away from any town. That soft river of light overhead is the flattened disk of stars viewed from the inside, and its glow fades into darkness somewhere around 50,000 light-years from the center in the direction we sit. For almost all of human history, that glow was the galaxy. There was nothing else to point at, nothing else anyone knew to look for. But past the place where the starlight thins away, there is a broader, fainter disk made not of stars but of cold hydrogen gas, reaching well beyond the final bright star, invisible to the eye, and detectable only once you learn to listen for it in radio waves. And past even that, wrapping the whole structure in a sphere far larger than either disk, there is a halo built mostly from matter that gives off no light at all, a presence we register only through its gravity, through the way distant stars move as if something enormous were holding them in place. 3 different edges. The edge of the light, the edge of the gas, the edge of the mass. They do not line up, they are not close to one another, and the gap between the nearest and the farthest is more than a factor of 10. When someone tells you the Milky Way is 100,000 light-years across, they are not wrong. They are describing the edge of the light. When someone else tells you it is nearly 2 million, they are not wrong either. They are describing the edge of the mass. Both are true, in the same breath, about the same galaxy, on the same quiet night. The word edge was carrying more weight than anyone noticed, standing in for a whole stack of separate boundaries, and each new generation handed a new way of seeing, reached a little deeper into that stack, and lifted out an edge the one before could not have known was there. The number never moved because the universe was keeping a secret from us. It moved because we kept learning to see more of what had been ours the whole time. There is a quieter fact folded inside that 2 million light-year figure. If the outer boundary of our galaxy really does lie near 950,000 light-years from the center, then the light now arriving from the farthest stars that still belong to the Milky Way left them before there was a single human being anywhere on Earth to one day catch it. Our entire species is only a few 100,000 years old. That light is older than all of us put together, and it is still, faintly, part of home. Every other galaxy we have ever measured cleanly, every tidy spiral with a diameter you can name, we measured from the outside, looking in. Ours is the single galaxy we can never step out of and turn around to face. We are inside it. We have always been inside it, working out the shape of a structure while standing somewhere in its middle, from nothing but the light that happens to find us. So before we can say how far the edge is, we have to answer something older and harder. How do you measure the size of a thing you have never once seen from the outside? Here is the trick William Herschel came up with, sometime in the 1780s, for measuring a galaxy he could never leave. If you cannot step outside the Milky Way to see its shape, then point your telescope in one direction and count every star you can see. Then swing to another direction and count again, and again, patiently, across the whole sky. Wherever you count more stars, the galaxy must run deeper, stretching farther out along that line before it ends. Wherever you count fewer, you are looking toward a nearer edge. The shape of the whole thing, he reasoned, should fall right out of the numbers, the way the outline of a dark forest reveals itself if you stand in the middle and note where the trees run thick and where they thin toward open ground. He and his sister Caroline worked through it night after night in the cold. He would sit at the mouth of a reflecting telescope some 20 feet long, about 6 meters, with a mirror nearly 19 inches across, and he would call out into the dark how many stars filled the small circle of sky in his eyepiece. Caroline sat below with the record book, catching each number as it came down to her, writing in the near dark, keeping the count while her brother's eyes stayed pressed to the sky. By the time they finished, they had gauged 683 separate patches of sky, and from those 683 numbers, Herschel drew the first real map anyone had ever made of the galaxy from the inside. The shape that emerged was a long, ragged sort of lens, wide across the middle and flattened at top and bottom, thick with stars along one great band, and thinning away above and below it. That much was close to right, closer than he could have known, because that flattened lens is more or less the disk we still talk about today. He had recovered the basic form of the Milky Way from nothing but starlight and arithmetic, working 2 centuries before anyone could check him against a photograph. For a first attempt with a homemade mirror and a notebook, it was an astonishing piece of reasoning. But there was a detail in his map that should have unsettled him, and it is the detail that matters most for us. Right near the center of that lens of stars, close to the heart of the whole system, sat the Sunday. Herschel's own star counts had placed us almost exactly in the middle of the galaxy. And whenever a measurement tells you that you happen to be sitting at the center of everything, that is the moment to grow suspicious, because the universe rarely arranges itself so flatteringly around the person doing the looking. The reason his counts came out that way runs quiet and deep, and it hangs on two assumptions he had to make and could not test. The first was that the stars are spread more or less evenly through space, so that counting them honestly reports how far the galaxy reaches in each direction. The second was that his telescope could actually see all the way to the edge, that the faintest stars he caught really were the last stars out there, with nothing but emptiness beyond them. Both assumptions felt reasonable. Both were wrong. And the second one was wrong in a way that quietly guaranteed he would find himself at the center no matter where he actually stood. Picture standing in the middle of a wide field on a foggy night, holding a lantern. The light reaches only so far before the fog swallows it, and so you can see the same modest distance in every direction, a soft circle of ground with you at its center. Turn any way you like. The circle turns with you, and you sit forever at the middle of it. Not because you are truly at the center of the field, which might stretch for miles unseen in every direction, but because the fog cuts off your sight at the same radius all around. Herschel was standing in exactly that kind of fog, though he did not know it was there, and so his counts fell away to nothing at roughly the same distance in every direction along the disk, and that even fade drew the sun neatly into the middle of a galaxy far larger than his map. There was a haze spread through the space between the stars, dimming the distant ones, erasing the faintest ones from his count entirely, and it fooled him into mistaking the reach of his telescope for the edge of the galaxy. He was not measuring where the stars stopped. He was measuring where his own sight gave out. And this is what stays with me about Herschel, because it is not a story of a man being careless. His logic was clean. His counts were careful. His sister's records were meticulous. The method was so sound that later astronomers spent more than a century refining the same basic idea, counting fainter and fainter stars with better and better telescopes, and for a long time they kept arriving at the same wrong answer, a modest galaxy with the sun near its heart. The flaw was never in the effort or the arithmetic. It sat in a single hidden assumption, the belief that the space between the stars was empty and clear, and that one buried assumption bent every conclusion that rested on top of it. It took an unusual kind of doubt to break out of that, the willingness to ask whether the very thing you are seeing through might be lying to you. For generations, no one seriously questioned it, because empty space looks empty, and there was no obvious reason to imagine an invisible substance thinning the light of far-off stars without ever announcing itself. The haze gave off no glow of its own. It cast no shadow you could point to. It simply, silently, made everything beyond a certain distance a little fainter than it should have been, and a little fainter reads, in a star count, as a little farther away, or as nothing at all. So the map of the galaxy stayed too small, and stayed centered on us, not for years but for lifetimes, held in place by something no telescope of the age could see. Everything after Herschel, every attempt to find the true edge, would first have to reckon with this quiet interference in the space between the stars. Someone would have to prove it was there at all, this invisible thing that had been shrinking the galaxy in every human map since the beginning. What was it? And how do you catch something that hides by doing nothing except making the distant stars look dimmer than they are? The thing that had been shrinking the galaxy in every human map was never caught by looking for it directly, because it could not be seen at all. It was caught, in 1930, by a man who set up two different ways to measure the same distance and waited to see whether they would agree. His name was Robert Trumpler, working at Lick Observatory in California, and the objects he chose to measure were open clusters, those loose gatherings of a few hundred young stars that drift through the disk of the Milky Way in family groups. What he did with them was quiet and clever, and it finally dragged the invisible thing into the light. Here is how you catch something that refuses to be seen. Trumpler measured the distance to each cluster twice, using two methods that had nothing to do with each other. The first method used brightness. If you know how much light a star truly gives off, and you see how faint it looks from here, the dimming tells you how far away it must be, since light fades with distance in a way we understand precisely. The second method used size. If you assume that open clusters are all roughly the same true width, then a cluster that looks small in the sky must be far, and one that looks large must be near, the same way a familiar object shrinks as it moves off down a road. Two rulers, two answers, and no reason on earth they should disagree. They disagreed. Every time, and always in the same direction. The brightness method kept reporting the clusters as farther away than the size method did, and the gap between the two answers grew steadily wider the deeper into the galaxy Trumpler looked. A cluster that its own dimness placed far out in the distance would still appear too large in the sky for that distance, as though it were much closer than its faintness claimed. By the plain logic of it, the distant clusters were being made to look fainter than they should, dimmed by something spread through the space between them and us, something that thickened with every additional stretch of distance the light had to cross. That something was dust. Not dust the way we mean it in a house, but grains far finer, scattered thinly through the space between the stars, so sparse that a single one of those grains might drift alone in a volume larger than a cathedral, and yet stretched across thousands of light years. The thin haze adds up until it swallows a serious fraction of the light passing through. Trumpler could put a number on it. Starlight crossing the plane of the galaxy lost roughly half its brightness for every 3,260 light years it traveled, dimmed by a bit under 1 step on the astronomer's scale of magnitudes per that distance. Half gone in the first stretch. Half of what remained gone in the next. Push toward the crowded heart of the galaxy, and the loss compounds until, in visible light, the center is not merely dim but entirely hidden, blotted out behind so many layers of intervening dust that no ordinary telescope has ever seen it directly. I find it strange and a little humbling that we live inside a galaxy whose center we cannot look at with our eyes. The brightest, densest, most crowded region of our whole system, tens of thousands of light years of stars packed toward the middle, sits behind a curtain we did not even know was hanging there until Trumpler measured its thickness. For every human being who ever looked up before 1930 and tried to reckon the size of the Milky Way, that curtain was quietly editing the sky, deleting the farthest stars from the count and dimming the ones that survived, and no one had proof it was there. The dust left a second fingerprint, and this one gave astronomers a way to map it. The fine grains do not block all colors of light equally. They scatter blue light more easily than red, so a distant star seen through a lot of dust arrives looking redder than it truly is, its blue stolen away along the path. You have watched the same physics at the end of every clear day, when the sun sits low and its light cuts a long slant through the thick air near the horizon, and the extra scattering strips the blue and leaves it burning orange and red. The dust between the stars does that to starlight, only across light years instead of miles, and the amount of reddening in a star's color became a gauge of how much dust lay between it and us. So the same haze that had fooled everyone became, once understood, a tool. The reddening told you how thick the dust was in any direction, which let you correct the dimming, which let you finally recover the true distances the dust had been hiding. When Trumpler's correction was applied, the distances measured out in the dusty disk fell into agreement with distances that had been measured a different way entirely, using objects that floated above the disk where the dust was thin. The galaxy stopped contradicting itself. Herschel's map had been too small because the dust cut his sight lines short. Every careful astronomer who followed him, refining the star counts for over a century, inherited the same invisible error, and their galaxies stayed too small and too centered on the sun for the same buried reason. It took someone willing to distrust the light itself to assume the photons arriving in his telescope had been tampered with on the way before the true scale could even begin to come loose. The lesson sitting underneath is uncomfortable. For 150 years, the thing most wrong with our picture of the galaxy was not something we had measured badly. It was something we had not known to include at all. But notice what Trumpler's fix quietly depended on. Those distances he checked his clusters against, the ones measured above the disk where the dust runs thin, someone had already found a way to gather them, years before the dust was ever proven. Someone had looked up out of the plane entirely at a set of ancient objects hanging far above and below the crowded, dusty midline of the galaxy, out where the view was clear. And what that person found in their arrangement had already done something no star count ever managed. It had taken the sun and shoved it hard out of the center of everything. How do you find the true middle of a galaxy whose middle you cannot even see? The way out of the fog was to stop looking through it. While the dust lay thick in the flat plane of the galaxy, hiding the center and cutting every sight line short, there were objects that floated clear above and below that plane, out where the haze thinned to almost nothing. Globular clusters, they are called. Dense balls of hundreds of thousands of ancient stars, packed so tightly they look like single fuzzy points until you turn a real telescope on them. They hang in a great swarm around the galaxy, most of them lifted out of the dusty midline, and because they sit above the fog, you can see them across enormous distances that ordinary disk stars could never survive. A young astronomer named Harlow Shapley realized that these clusters, precisely because they escape the dust, might reveal the shape of the whole galaxy in a way the buried disk stars never could. He worked at Mount Wilson in California through the middle 1910s on a telescope with a 60-inch mirror, the largest in the world at the time. His tool for distance was a kind of star that keeps its own time. Certain stars pulse, brightening and dimming in a steady rhythm, and a woman named Henrietta Leavitt had discovered that the slower a star of this type pulses, the more light it truly gives off, with a precision you could calibrate. Find one of those pulsing stars inside a globular cluster, time its rhythm, and its rhythm tells you how bright it really is. And comparing that to how faint it looks tells you how far away the whole cluster sits. Shapley found these timekeeping stars inside cluster after cluster and began, one by one, to pin down their distances. By 1918, he had measured 69 of them, and he laid their positions out in space to see the shape they made. What he found should have been impossible under the old picture of the galaxy. The clusters were not spread evenly around the sun, the way they would be if we sat at the middle of things. They were piled up overwhelmingly toward one side of the sky, crowded thick in the direction of the constellation Sagittarius, and sparse in the opposite direction. 2/3 of them hung over a single region, as though the whole swarm were orbiting some point far away from us, off in the direction where they clustered thickest. Shapley made the leap that the point they swarmed around was the true center of the galaxy. If the clusters formed a great sphere, and that sphere was centered tens of thousands of light-years away toward Sagittarius, then the Sun was not at the heart of the Milky Way at all. We were far out toward one edge, riding in the thin outskirts, looking in toward a center we had never suspected was so distant. With a single map of 69 fuzzy balls of ancient stars, he had taken the Sun and shoved it out of the middle of creation, out to a lonely suburb tens of thousands of light-years from the action. The direction he pointed to was right, and the modern measurement puts that center about 27,000 light-years away, still toward Sagittarius, exactly where Shapley aimed. When you look up on a summer night at the brightest, densest part of the Milky Way, that thick, glowing region in Sagittarius, you are looking toward the center he found, though the core itself stays hidden behind the very dust we have been tracking. He got the hardest part, the part that overturned the human place in the galaxy, essentially correct. Working 100 years ago with a single telescope and a handful of pulsing stars. And then he overshot. The same map that correctly moved the Sun also came back with a galaxy far too large, a Milky Way that Shapley measured at around 300,000 light-years across, roughly 3 times wider than the disk we now recognize. 2 separate errors pushed him too far, and both are the kind of honest mistake that runs through this whole story. He had not yet corrected for the dust, the same haze that would not be proven for another 12 years, and even the clusters lifted above the plane were dimmed a little by the thin fog near the disk, which nudged his distances outward. Worse, the pulsing stars he used came in 2 different kinds that he had not yet learned to tell apart, and he treated the fainter kind as though they were the brighter kind, which threw his distances off in the same outward direction. The edge of the galaxy did not only ever grow. This once, it grew too much, and later work had to pull it back inward, shrinking Shapley's 300,000 light-years down toward the 100,000 we use for the disk today. The number moved in both directions across the years, overshooting here, creeping outward there, and that untidiness is the honest texture of how we actually came to know the size of our home. It was never a clean march toward a bigger and bigger answer. It was a long argument, full of corrections that ran both ways, each one loosening a different hidden assumption. What Shapley could not have known was how large his mistake about size would loom in the very next fight. His big galaxy was so enormous, 300,000 light-years of stars, that he became convinced it must be the entire universe, with nothing beyond its edge but empty space. And that conviction ran him straight into the faint spiral smudges scattered across the sky, the little whirlpools of light that some astronomers had begun to suspect were not part of the Milky Way at all, but separate galaxies of their own, unimaginably far away. If Shapley was right that our galaxy filled the universe, those spirals had to lie inside it. If he was wrong, then the edge of the Milky Way was not the edge of everything, and each of those smudges was another island of stars floating in a darkness far vaster than anyone was ready to accept. Which was it? Were those faint spirals inside our galaxy, or unthinkably far beyond its edge? For a few years, one honest question had no answer, and the whole scale of reality hung on it. Scattered across the sky were faint spiral smudges, little whirlpools of pale light, and no one could say whether they were small clouds of gas drifting inside our own galaxy or separate galaxies of their own, so far away that their stars blurred together into haze. If they were inside the Milky Way, then our galaxy might well be the whole of creation, with nothing beyond its edge but empty dark. If they were outside, then the edge of the Milky Way was not the edge of everything, and each smudge was another island of 100 billion stars, floating in an ocean nobody had dared to imagine. The argument came to a head on a spring evening in 1920, at a meeting in Washington, in what later got called the Great Debate. Two astronomers stood up in turn to make the opposing cases. Harlow Shapley, the same man who had just moved the sun out to the galaxy's edge, argued that the Milky Way was enormous, so enormous it must be essentially the entire universe, and those spiral smudges were nearby wisps belonging to it. Heber Curtis argued the reverse, that the galaxy was more modest in size, and that the spirals were distant island universes, separate galaxies as grand as our own, unimaginably far beyond us. What makes that night worth returning to is that neither man won, because neither was fully right. Shapley was correct that the galaxy was large and that we sat far from its center, the very thing his globular clusters had shown. Curtis was correct that the spirals were separate galaxies, that the Milky Way was one island among countless others. Each held one true half of the answer and pressed it against the other man's false half, and the audience, swayed more by Curtis, the smoother speaker, drifted toward calling him the winner, though the real verdict was that the question simply was not settled yet. It could not be settled by argument at all. It needed a measurement no one had yet made. That measurement came 3 years later, and it came down to a single pulsing star. Edwin Hubble had arrived at Mount Wilson just as a new telescope came online, a giant with a mirror 100 inches across, about 2.5 meters, the largest in the world. On the night of October 5th into the 6th, 1923, in poor observing conditions, he aimed it at the Great Spiral in Andromeda and held the exposure open for 45 minutes, long enough that the blur began to break apart into individual points of light. Stars. Actual separate stars, in a thing that had only ever been a smudge. Comparing his new plate against earlier ones, Hubble picked out 3 points that seemed to have flared up like novae, and he inked a small letter N beside each one on the glass. Then he looked harder at one of them. It was not flaring once and fading, the way a nova does. It was rising and falling in a steady, repeating rhythm, brightening and dimming on a regular beat. It was one of the pulsing timekeeper stars, a Cepheid, the exact kind Shapley had used to measure his clusters, the kind whose rhythm reveals its true brightness. On the plate, Hubble crossed out the N he had written beside it and wrote instead, in a quick hand with an exclamation point, the word for variable. That small correction on a piece of glass redrew the size of the universe. Because the moment he knew it was a Cepheid, Hubble could read its rhythm, learn its true brightness, compare that to how heartbreakingly faint it looked, and calculate the distance to the star, and therefore to the whole spiral around it. The number he got was about 930,000 light-years. By our modern measurements, that was actually far too small, less than half the true distance to Andromeda, which sits around 2.5 million light-years away. But even his underestimate was more than 3 times larger than Shapley's entire universe. Wrong as the exact figure was, it landed hopelessly, unarguably outside any possible edge of the Milky Way. Andromeda was not inside our galaxy. It was another galaxy entirely, a separate continent of stars, and if it was out there, so were all the others. Thousands upon thousands of the faint spirals, each one its own island. In a single night's work, the universe stopped being one galaxy and became a sky full of them, with the Milky Way reduced to just one among a countless scattering. There is a human moment folded into this that I keep close. When Hubble sent word of the Cepheid to Shapley, who had built his career on the idea of a single all-encompassing galaxy, Shapley is said to have looked at the letter and remarked, quietly, that here was the thing that had destroyed his universe. He had been the one to move the sun off center, to enlarge the galaxy beyond anyone's imagining, and now a younger man was using Shapley's own pulsing stars to shrink that galaxy back into one small island in an endless sea. And to his lasting credit, Shapley looked at the evidence and changed his mind, gave up the universe he had fought for, because the measurement left him no honest choice. For our question, this night changed what the word edge even means. Before Hubble's plate, the edge of the Milky Way might have been the edge of all existence, the shoreline of everything. After it, the edge became something smaller and stranger, a real border between our own galaxy and the vast dark gulf separating us from the next one. Finding that border now mattered more than ever, because it was the line between home and everything else. But every tool that had brought us this far shared one deep weakness, and it is the weakness that has haunted this whole story from the beginning. Star counts, globular clusters, pulsing Cepheids. Every one of them worked by catching visible light, and visible light is the exact thing the dust devours. To trace the galaxy's true edge, we would need to find its faint outer reaches where the stars themselves give out, where there may be almost nothing left that shines at all. What if the Milky Way stretches on past the final star, out into regions where nothing glows? How would we ever find an edge made of something that gives off no light for us to see? The way past the dust was to stop using light at all. Every tool in this story so far, the star counts, the globular clusters, the pulsing Cepheids, had one thing in common, and it was the thing the dust could defeat. They all worked by gathering visible light, the same light the dust scatters and swallows. To see the galaxy whole, past the fog, someone would have to find a signal that could pass straight through the dust as if it were not there. That signal was already streaming through you, through the walls, through the whole Earth, and no one had learned to hear it yet. It comes from the most common thing in the universe, a single hydrogen atom, one lonely electron circling one proton. Both the electron and the proton behave like tiny spinning magnets, and they can spin in two arrangements, either lined up the same way or pointed opposite. The two arrangements hold very slightly different amounts of energy, and every so often an atom sitting in the aligned, higher state flips to the opposite, lower one, and releases that tiny sliver of extra energy as a faint pulse of radio waves. The pulse always comes out at exactly the same wavelength, close to 21 centimeters, about 8 inches, a precise radio note sounded by hydrogen everywhere in the cosmos. What makes this almost unbelievable is how rarely any single atom does it. A given hydrogen atom, left alone, might wait millions of years before it flips even once. If the galaxy held only a modest amount of hydrogen, the signal would be far too faint for anything to catch. But the space between the stars is filled with vast, cold clouds of hydrogen, unimaginable numbers of atoms drifting in the dark, and across so many of them there are always some flipping at every instant, so that the faint individual pulses add together into a steady radio hum pouring out of the whole galaxy at that one exact wavelength. The Milky Way has been quietly singing this one note the entire time, and we simply had no ear for it. A young Dutch student named Hendrik van de Hulst worked out that this note should exist, on paper, in 1944, during the war, when his mentor Jan Oort was searching for any way to map the galaxy through the dust. Van de Hulst calculated the wavelength but doubted, in print, whether the signal would ever be strong enough to detect. It took another 7 years and a homemade instrument to prove him too pessimistic. At Harvard, a graduate student named Harold Ewan built a receiver for that one radio note, working nights and weekends under his advisor Edward Purcell. The antenna was a horn shape, partly made of plywood sheathed in copper, and there was nowhere proper to mount it, so they simply pushed it out through a window on the 4th floor of the physics building and pointed it at the sky over the rooftops. On the 25th of March, 1951, that plywood horn caught the hum. The most common atom in the universe, calling out at its one wavelength, picked up by a contraption sticking out of a laboratory window. Within weeks, groups in the Netherlands and Australia confirmed it, and a new way of seeing the sky came into the world. The reason this signal changes everything is that radio waves this long pass through the dust untouched. Think about driving through thick fog with the radio on. The fog stops your headlights cold because visible light waves are about the same size as the fog droplets and get scattered every direction. But the radio in your car plays on without a stutter because radio waves are far too long to notice something as small as a droplet and simply flow around it. The grains of interstellar dust are tiny, comparable in size to the wavelength of visible light, which is why they scatter starlight so effectively. The 21-centimeter hydrogen signal has a wavelength hundreds of thousands of times longer than visible light, enormously larger than any dust grain, so it slides through the entire dusty disk as though the fog were not there. For the first time, we could map the galaxy all the way through, center included, edge included, no curtain in the way. And when astronomers tuned into the hydrogen and traced where it lay, the map they drew was larger than the one made of stars. The hydrogen gas did not stop where the last bright stars stopped. It kept going, a broad, thin disk of cold gas reaching well beyond the edge of the starlight, in places stretching to nearly twice the radius of the visible disk of stars. The galaxy had an outer region made almost entirely of gas, dark and starless, that no amount of looking with visible light could ever have revealed. The edge moved outward again. The disk of stars, the thing everyone had spent a century measuring, turned out to be only the bright inner portion of something wider. Past the final stars, there was still galaxy, still material orbiting the center, still structure, made of gas instead of suns and utterly invisible to the eye. And the hydrogen map showed something else in that outer gas, a strange bending where the far reaches of the disk curl up on one side and down on the other, warped out of the flat plane like the brim of a hat. I keep returning to what this shift really meant for us, the moment astronomy stopped being only about light in the eye. For all of human history, to study the sky was to catch light, whether with an eye or a photographic plate. Now, the most complete early map of our own galaxy came not from any picture at all, but from listening to a hum, tuning a radio to the faint, patient note of hydrogen atoms flipping their spins across thousands of light years. We had been blind in one narrow band and calling it sight. The galaxy was always broadcasting more of itself than our eyes could receive. But the hydrogen brought a puzzle as large as the view it opened. Out in that far gas disk, well beyond the stars, the astronomers could measure not just where the gas was, but how fast it moved, because the radio note shifts slightly in pitch depending on whether the gas races toward us or away. And the gas at the outer edge was moving fast, far too fast, whipping around the center at speeds the visible galaxy had no business sustaining. By everything we understood about gravity, gas that far out, with so few stars around it, should have been drifting slowly, barely held. Instead, it was tearing along as though gripped by an enormous mass that simply was not there in any light we could see. What was holding it? What could grip the outer galaxy hard enough to move it that fast, while giving off no light at all? The thing gripping that outer gas turned out to be the largest part of the galaxy, and it is the part no telescope has ever seen. We found it not by looking at it, because there is nothing to look at, but by watching how it makes everything else move. The clue was in the speed of the outer galaxy, the very thing the hydrogen radio maps had measured. And once astronomers understood what that speed implied, the size of the Milky Way had to be rewritten one more time, larger than anyone had dared. To feel why the speed was so alarming, look at our own solar system, where the rule is simple and clean. Nearly all the mass sits in one place, the Sun at the center, and the planets orbit that central weight. Because gravity weakens with distance, the planets far from the Sun move slowly, and the ones close in move fast. The innermost planet races around at nearly 50 kilometers a second, while the outermost crawls along at barely a tenth of that speed, dawdling through the cold because the Sun's grip out there is so faint. That is how orbits work when the mass is piled in the middle. The farther out you go, the slower things must move to stay in their paths. A galaxy has its light piled in the middle too, its bright bulge of stars packed toward the center, thinning out toward the dark rim. So, the outer stars and gas should behave like the outer planets, orbiting slowly, lagging behind, because most of the glowing mass lies far inside them. The rotation speed should climb near the center and then fall away toward the edge, dropping off exactly as it does across the solar system. That was the firm expectation, grounded in the same gravity that governs the planets, and it is what everyone assumed the galaxies would show once someone measured them carefully. Vera Cooper-Rubin measured them carefully. Working with the instrument maker Kent Ford, who had built a spectrograph far more sensitive than anything before it, she set out in the late 1960s to chart how fast the gas orbits at different distances out from the center of the Andromeda galaxy, our large spiral neighbor. She split the faint light from glowing gas clouds into its spectrum and read the tiny shifts in that light, shifts that reveal how fast each cloud is moving toward us or away, and from those she built the orbital speed at each distance from the center. The result, published in 1970, refused to fall. The outer gas was not slowing down. Far past the bright inner disk, out where the starlight faded and the visible galaxy thinned to almost nothing, the gas kept right on orbiting at nearly the same enormous speed, around 250 kilometers a second, more than 500,000 miles an hour, holding that pace steadily out to the very limit of what she could measure. Later radio observations pushed the measurement even farther out, into the faint hydrogen beyond the stars, and the speed stayed flat there too, unwavering, mile after mile into the dark. Where the curve should have curved downward, sliding toward zero, it simply ran level, as though the outskirts had never heard that the mass was supposed to be behind them. There is only one way gravity permits this. If the outer gas moves that fast and is not flung away into intergalactic space, then there must be enormous mass out there holding it, mass that keeps piling up the farther out you go, long after the light has run out. The stars and gas we can see fall away toward the rim, but the total mass does not fall away with them. It keeps increasing, out past the last star, held in something that gives off no light, no radio hum, no signal of any kind that we have ever caught directly. We register it only through its grip, through the speed it forces onto everything we can see. That invisible mass got the name dark matter, and I want to be careful about what we actually know of it, because the honesty here matters. We do not know what it is. We have never held a piece of it, never caught it in any instrument, never identified a single particle of it with certainty. What we know is that the galaxies do not spin the way their visible mass says they should, and that the same discrepancy appears in galaxy after galaxy, in the way whole clusters move, in the way light bends around them. The missing mass is not a guess pulled from nowhere. It is measured over and over by its gravitational effect. What remains unknown is its nature, not its presence. Rubin knew that one galaxy could be a fluke, so she and Ford spent years measuring more, spiral after spiral, large and small. And by 1980 they had charted 21 of them, and the flat curve appeared in every one. The outer regions of galaxy after galaxy were moving as though gripped by far more mass than any telescope could find. Decades earlier, an astronomer named Fritz Zwicky had noticed the same shortfall in a great cluster of galaxies, whole galaxies swarming too fast for the visible mass to hold, and he had spoken of missing mass then, in the 1930s, and been largely set aside. It took Rubin's patient wall of evidence, one rotation curve at a time, before the community accepted that most of the mass in the universe is something we cannot see. For our own galaxy, this is the third edge, and the largest by far. Every photograph you have ever seen of the Milky Way, every glowing spiral with its arms and its bright core, shows only the luminous minority, the small fraction of the galaxy that happens to shine. Wrapped around all of it, reaching far beyond the disk of stars and even beyond the wider disk of gas, is a vast sphere of dark matter, and by mass, it is most of what the Milky Way actually is. The galaxy we can see is a bright ornament hanging at the center of a dark thing far larger. The real edge, the edge of the mass, lies somewhere out in that darkness, which leaves us chasing the strangest measurement in this whole story. We now have to find the size and the boundary of the largest part of our galaxy, a part that emits nothing, reflects nothing, blocks nothing, a part known only by the pull it exerts. You cannot photograph it, cannot map its light, cannot listen for its hum. How do you draw the edge of something that has never given off a single trace of itself, and only ever makes its presence known by moving the things you can see? You have seen pictures of the Milky Way your whole life, and not one of them showed you the galaxy. They showed the bright part, the spiral of stars, the glowing core, the dust lanes threading through the arms. By mass, all of that together is the small minority of what our galaxy actually is. The real Milky Way, the thing that holds the stars in their orbits and sets the speed of the outer gas, is a vast sphere of dark matter, and no photograph has ever shown it, because there is nothing there for light to catch. Start with the weight, because the weight is what gives it away. When astronomers measure the total mass of the Milky Way now, using the motions of distant objects swinging around it, the number comes out near 1.5 trillion times the mass of the Sunday. The stars, all 200 billion of them, plus the gas and dust woven between them, come to something like 60 billion solar masses when you add it all up. Set those two numbers beside each other and the everyday galaxy, the entire glowing thing we have spent this whole story learning to measure, accounts for only a few % of the mass. The other 90% and more is dark, invisible, and spread through a region far larger than the disk of stars. Even the famous monster at the center barely registers. The supermassive black hole in the heart of the galaxy, the one that makes headlines, weighs about 4 million solar masses, and against the 1.5 trillion of the whole galaxy, it is less than a millionth of the total. A rounding error at the bottom of the ledger. The thing that dominates our galaxy by mass is not the black hole, not the stars, not the gas. It is the dark halo, and we have never seen it, and we do not know what it is made of. So the question becomes how anyone can measure the size of a thing that gives off nothing, and the answer is the same trick that revealed it in the first place. You cannot see the halo, but you can see things falling through it. Scattered far out beyond the disk are objects that orbit the galaxy at enormous distances, the globular clusters lifted high above the plane, and beyond them the small satellite galaxies that circle the Milky Way like moons around a world. Each of those objects is a weight dropped into the invisible well, and by clocking how fast it moves and how its path curves, astronomers can work out how much mass must lie inside its orbit to bend it that way. Map enough of them at enough different distances, and the invisible mass draws its own portrait, ring by ring, out into the dark. There is a cleaner version of the same idea, and it measures the depth of the well directly. For any speed, there is a limit called the escape velocity, the speed something would need to break free of the galaxy's gravity entirely and never fall back. If you find the fastest moving stars near us that are still bound to the galaxy, still looping around rather than flying away forever, their speed tells you how deep the gravitational well must be to hold them. That speed, measured near the Sun, comes out above 500 kilometers a second, well over 1,000,000 miles an hour, and a well that deep cannot be dug by the visible stars alone. It takes the full weight of the dark halo to hold a fast star in, the same way you can judge the depth of a well you cannot see into by how hard you must throw a stone to clear the far rim. When you follow those measurements outward, the dark halo reaches to something like 1,000,000 light-years from the center, roughly 10 times the span of the disk of stars we started with. The bright galaxy in every photograph sits at the center of that dark sphere like a coin at the center of a stadium, small, luminous, and vastly outweighed by the darkness around it. The edge of the mass, the third and largest of our three edges, lies out there in that invisible sphere, and it is the edge that comes closest to answering how far the Milky Way truly reaches. There is one thing we can weigh far better than we can picture, and honesty demands I say so plainly. We can measure how much dark matter surrounds us, and roughly how far it extends, with real confidence. Its exact shape is another matter, still argued over. Whether the halo is a clean sphere, or squashed like a flattened ball, or slightly lumpy and lopsided from the galaxies it has swallowed, remains genuinely unsettled, because reading the three-dimensional shape of an invisible thing from the paths of a scattered handful of orbiting objects is close to the hardest measurement in the field. We know it is there. We know about how big it is. What it looks like, we are still working out. Now let this settle over where you are lying. You are not merely inside the disk of stars. You are deep inside the dark halo, near its very center, suspended in the densest part of the largest structure you will ever occupy, and it is a structure you cannot see and have never seen drawn correctly. If the dark matter is made of particles, as many physicists suspect, then those particles are passing through the room right now, through the walls, through the bed, through your body, streaming through the earth as though it were not there, felt by nothing, stopped by nothing. Trillions of them may have drifted through you in the time it took to breathe once, and you have never sensed a single one. We live our whole lives inside this thing. Every human who has ever looked up at the Milky Way was looking out from deep within a dark sphere 10 times wider than the band of light they could see, mistaking the glowing minority for the whole. The galaxy you can see is the small, bright heart of a far larger galaxy you cannot, and the edge we have been chasing all along lives out in the part that never shines. To find that edge, To trace the true shape and reach of the dark halo, we need something better than a scattered handful of orbiting clusters. We need a probe that falls all the way through the halo and records the shape of its pull along the entire path, a long, delicate thing stretched across the darkness that remembers every tug. And it happens that the galaxy makes these probes itself out of smaller galaxies it captures and slowly tears apart. When a little galaxy wanders too close and the Milky Way's gravity pulls it into a long, thin ribbon of stars, that ribbon traces the invisible pull with exquisite precision, like a thread drawn through the dark. How do you read the shape of something invisible from the wreckage of the galaxies it has destroyed? The finest instrument we have for measuring the dark halo is a galaxy being torn to pieces. Small galaxies orbit the Milky Way, and when one of them wanders too close, our galaxy does not swallow it whole in a single gulp. It pulls the little galaxy apart slowly, stretching it into a long, thin ribbon of stars strung out along its orbit, and that ribbon becomes a line drawn through the darkness, tracing the exact path the galaxy took as it fell. Read the shape of that line, and you are reading the shape of the invisible pull that drew it. To see why a galaxy stretches instead of simply falling, think about how the moon raises the tides. The moon pulls a little harder on the near side of the Earth than on the far side, because gravity weakens with distance, and that small difference across the width of the Earth is enough to lift the oceans into bulges. Now do the same to a small galaxy sitting in the Milky Way's gravity. The near edge of the dwarf feels a stronger pull than the far edge, and that difference stretches the whole thing out along the direction of its fall, drawing stars off the front and off the back, until the dwarf unravels into two long trailing arms. The word for this stretching is tidal, the very same word, because it is the very same physics that swells the sea, only worked on a galaxy instead of an ocean. In 1994, 3 astronomers, Rodrigo Ibada, Gerard Gilmore, and Michael Irwin, stumbled onto one of these dying galaxies almost by accident, hiding nearly behind the center of the Milky Way. It is called the Sagittarius Dwarf, and it had gone unnoticed until then because it sits on the far side of the crowded galactic core, camouflaged among the dense star fields. A whole galaxy being devoured in our own backyard, and we had walked past it for the entire history of astronomy without seeing it. By the time it was found, it was already coming apart, its stars pulled into streams that we have since traced, looping more than once around the entire sky. That stream is the plumb line we needed. The stars torn off the dwarf follow almost exactly the orbit the dwarf itself traveled, so the full ribbon is a record of a single path threading through the halo, out to distances of several 100,000 light-years and back. Because the dark matter is what bends that path, the shape of the stream carries the fingerprint of the dark matter's shape. A stream falling through a perfectly round halo would trace one kind of curve, staying neatly in a single plane, while a stream falling through a squashed or lopsided halo would twist and drift out of its plane in a particular way. The stars themselves are the test masses, dropped into the invisible well not by us but by gravity, recording the shape of the pull along every step of the fall. And here the honesty of the science shows through, because the answer has not come out clean. Different teams, studying the same Sagittarius stream with different assumptions, have pulled out different shapes for the dark halo. Some analyses find it stretched out like a rugby ball, some find it flattened like a squashed sphere, and some find it fully lopsided, tilted in 3 directions at once. The stream that was supposed to settle the halo's shape has instead handed us 3 contradictory answers, and the disagreement is not a sign that the method is broken. It is a sign of how genuinely hard it is to read the 3-dimensional form of an invisible thing from a single thread of stars, and of something else that took years to appreciate, that the halo may not be sitting still to be measured. The trouble has a name, and it is the largest of the Milky Way's companions, the Large Magellanic Cloud. For a long time we pictured the two Magellanic Clouds, those bright smudges in the southern sky, as old and faithful satellites that had circled the Milky Way for billions of years. Then astronomers measured how fast they are actually moving, tracking their tiny drift across the sky over years. And the speed came out surprisingly high, high enough that the clouds may not be long-term companions at all, but newcomers falling toward us for the very first time. That measurement is still debated, still being refined, but if it holds, it changes the picture. Because a massive newcomer like the Large Magellanic Cloud does not just orbit quietly. It pulls hard enough to tug the whole Milky Way, shifting our galaxy's center and yanking on the very streams we use to measure the halo, which is part of why those streams keep giving different shapes. So the picture we are left with is not a still portrait but a system in motion, mid-event. The Sagittarius dwarf is dying now, its stars being stripped away as we watch. The Magellanic Clouds are falling in now, dragging the galaxy off balance as they come. The halo we are trying to measure is being stirred by the very objects we are using to measure it, and every number we extract is a snapshot of something that will look different in 100 million years. We are not weighing a fixed object on a scale. We are reading the motion of a galaxy still in the middle of assembling itself. There is something I keep close about all of this, about how we come to know the shape of the dark. The only reason we can trace the invisible halo at all is that it is destroying things, tearing small galaxies into ribbons, and the ribbons are what let us see. We learn the form of the unseen from the wreckage it leaves, from the galaxies it has pulled apart and the ones it is pulling apart right now. The dwarf's death is our measuring instrument, and it did not consent to the role. A galaxy is coming apart above us tonight so that we can begin to know the shape of the thing coming apart it. But every stream we have is still only a scattered handful of stars, picked out of an enormous crowd, and each one traces just a single path through the halo. To map the outer galaxy fully, to catch not one falling ribbon but the motion of the whole vast population of stars at once, we would need to measure the precise position and speed of not thousands of stars, but hundreds of millions, each one pinned down with a precision no telescope had ever reached. That sounds impossible, and until very recently it was. What would the edge of the galaxy look like if you could track the exact motion of 1 billion stars at the same time? For all of this history, we measured the galaxy a handful of stars at a time. A few hundred counted by Herschel, 69 clusters mapped by Shapley, 1 pulsing star on Hubble's plate, a scattered ribbon of stars torn from a dying dwarf. Then, in the last decade, a single machine measured nearly 2 billion of them, and did it with a precision that turns the whole outer galaxy from a blur into a place with an address. The machine was called Gaia, a spacecraft the Europeans launched in December of 2013 and parked far from Earth, where it spun slowly and stared at the sky, sweeping the same stars again and again for more than 11 years. It did one thing, and did it better than anything before it. It measured exactly where each star sits and exactly how it moves. Over the mission, it gathered more than 3 trillion separate measurements, charting close to 2 billion stars, about 1 in every 100 stars in the Milky Way, until it ran out of fuel and was switched off at the start of 2025. The precision is the part that is hard to hold in the mind. Gaia could detect a shift in a star's position so small that it compares to picking out the width of a single human hair held up more than 5,000 kilometers away, roughly 3,000 miles, about the distance across the Atlantic Ocean. It needed that fineness because the measurement it depends on is tiny. As the spacecraft moves through space, nearby stars appear to shift ever so slightly against the far more distant background, the way a finger held up at arm's length jumps back and forth when you look with one eye and then the other. The size of that shift gives the true distance to the star, and tracking it over years gives the star's real motion through space, and doing this for 2 billion stars at once produces something no one had ever held before. A three-dimensional map of the galaxy with the clock running. With that map, you can do something close to time travel. Since Gaia records not just where the stars are, but how they move, you can take their motions and run them backward, rewinding the positions of millions of stars to see where they have been. And when astronomers did this, a ghost rose out of the data. A huge group of stars, scattered all across the sky, turned out to be moving together in a strange, stretched-out pattern, all sharing the same peculiar orbits, all bearing the chemical signature of a birthplace that was not our galaxy. They were the remains of another galaxy entirely, one that fell into the Milky Way and was devoured around 10 billion years ago. This lost galaxy has a name now, Gaia Enceladus, and at the time of the collision, it was something like a quarter the size of the young Milky Way, a major impact rather than a minor snack. An astronomer named Amina Helmi and her colleagues matched the pattern of these stars against simulations of galaxy collisions and found that the wreckage lined up, that this really was the debris of an ancient merger still ringing through the galaxy today. Much of the inner halo, the sphere of old stars around us, is built from the shattered body of that swallowed galaxy. When you look at those particular halo stars, you are looking at the scattered remains of a world that died before the sun was born, its stars folded into ours so long ago that they have been orbiting alongside us for most of the age of the universe. This is what people mean by galactic archaeology, and it captures something I keep close about Gaia. We are reading a collision that happened 10 billion years ago from the way stars move tonight, reconstructing an ancient event no one witnessed from the faint memory it left in a billion orbits. The stars are witnesses, and their velocities are the testimony, and a machine patient enough to clock all of them at once can finally take that testimony down and solve a crime that went cold before there was a planet here to notice it. But Gaia did not only reach outward and backward. It also unsettled the most familiar edge of all, the disk of stars right under our feet. For a century, the disk had a comfortable size, about 100,000 light-years across, the number we started this whole story with. Then careful surveys, using Gaia together with other instruments, began finding disk stars farther out than the disk was supposed to reach, stars that belong to the flat rotating disk sitting well beyond its assumed rim. Some of that work suggests the stellar disk may stretch closer to twice the old figure, though how far it truly extends is still being argued over, because the outer disk fades so gradually that where you draw its edge depends on how faint a star you are willing to chase. So even the innermost, best-known edge would not hold still. The disk we thought we had measured 100 years ago turned out to have more of itself waiting past the line we had drawn, exactly as every other edge in this story had. Gaia pushed the outer boundaries and pulled at the inner ones at the same time, and the galaxy came out larger and stranger from both directions at once. The warped disk was found to wobble like a spinning top. The halo turned out to be stitched together from swallowed galaxies, and the tidy numbers softened into ranges and arguments. The more precisely we measured, the less the galaxy agreed to have a single clean size. Now, with a billion stars carrying addresses and velocities, one old question comes back with a sharp new edge on it. We can finally start to ask, precisely, Which star is the farthest one that still belongs to us? Not the farthest star we can see, but the farthest one still held by the Milky Way's gravity, still bound to this galaxy rather than drifting free in the dark between galaxies. Somewhere out there is a last star, faint and alone, near the true edge of everything we can call home. How far away does it lie? And how could we ever know that a single lonely star, halfway to another galaxy, still belongs to ours? The farthest stars known to belong to the Milky Way were found by accident in a picture of somewhere else. A survey pointed its telescope at the Virgo cluster, a swarm of galaxies far beyond our own, and in the foreground of that distant scene, scattered faintly across the frame, sat stars that turned out to be members of our own galaxy's outermost halo. A graduate student named Yuting Feng, working with the astronomer Raja Guha Thakurta, pulled 208 of them out of data, meant for something else entirely, and the farthest one lies more than 1 million light-years from Earth, almost halfway to Andromeda. To understand how a star that remote can be measured at all, you have to know what kind of star these are. They are called RR Lyrae stars, ancient things, more than 10 billion years old, and they pulse, swelling and shrinking in a steady beat, much like the Cepheids that Hubble used, though fainter and older. The rhythm of that pulse is tied to the star's true brightness, so once you catch the beat, you know how much light the star really pours out. Compare that to how dim it looks from here, and the gap between the two gives you the distance, cleanly, across 1 million light-years of dark. These old pulsing stars are lighthouses, and their steady flashing let Feng measure just how far the halo of our galaxy reaches. It reaches farther than almost anyone is ready to picture. The 208 stars spread outward from around 60,000 light-years all the way to more than 1 million, and that farthest one sits at nearly half the distance to the Andromeda galaxy. Remember that the disk of stars, the bright familiar Milky Way, is only about 100,000 light-years across. These halo stars are 10 times farther out than the edge of that disk, faint and ancient and unthinkably isolated, each one drifting through a darkness so empty that its nearest stellar neighbor may be thousands of light-years away. And this forces a strange and beautiful question, one that has quietly haunted the whole idea of an edge. What does it even mean for a star that far away to belong to the Milky Way? A star 1 million light-years out is nowhere near the disk, nowhere near the crowded glow we call our galaxy, sitting alone in the black gulf between us and Andromeda. On what grounds do we still call it ours? The answer is that belonging, out here, has nothing to do with location anymore. A star belongs to the Milky Way if the galaxy's gravity still holds it, if it is moving slowly enough to remain bound, looping on some enormous orbit, rather than flying away into intergalactic space forever. Earlier, we talked about escape velocity, the speed something would need to break free of the galaxy entirely. A star still moving slower than that limit, however far out it drifts, is still captured, still falling around the galaxy on a leash of gravity light-years long. That is the real edge of the stars, not a place, but a condition, the line between what the Milky Way can still hold and what has slipped its grip. There is something in that reframing I keep close, because it quietly changes what home means. A star out there in the emptiness, with no other star near it, no glow around it, nothing at all to mark it as part of anything, is still ours for one reason only, that our galaxy's gravity has not let go of it. Home is not where the star sits. Home is what still holds it. By that measure, the Milky Way extends its claim over stars so far away and so alone that they might as well be adrift in the void, and yet they are not adrift, because something they cannot see still keeps them. But this is exactly where the whole notion of a clean edge begins to dissolve, and the astronomers who found these stars said so plainly. If our stars reach out 1,000,000 light-years toward Andromeda, and the halo they belong to stretches at least that far in every direction, then our galaxy is far larger than its bright disk ever suggested. And Andromeda is not a small galaxy sitting politely at a safe distance. Andromeda is roughly our equal, just as large, with its own vast halo of stars reaching out toward us the same way ours reaches toward it. Guha Thakurta put the consequence bluntly, that the two galaxies are both so enormous, there is hardly any empty space left between them at all. Sit with where that leaves us. We started this journey with a disk 100,000 light-years across, a tidy island with a clear rim. Now the stars that still belong to us run out to 1,000,000 light-years, nearly touching the territory of the next great galaxy, and the gulf we imagined between the Milky Way and Andromeda, that vast, lonely emptiness, is being crowded from both sides by two overlapping halos of ancient stars. The edge has not just moved outward again. It has moved so far outward that it is starting to run into the edge of someone else. And stars are only the part of this we can see. Around every large galaxy, reaching even farther than its most distant stars, there is something else, an enormous invisible halo of thin gas, far more extensive than the stellar halo, stretching out into the dark toward the neighboring galaxies. If the stars already reach halfway to Andromeda, that gas may reach farther still. Which raises a question that should be impossible, and is not. If our gas stretches toward Andromeda, and Andromeda's gas stretches toward us, is there any empty space left between the two galaxies at all, or have they already, quietly, begun to touch? Beyond the farthest stars, every large galaxy is wrapped in something even larger and far harder to see, an enormous halo of thin gas reaching out into the dark long after the stars have run out. It has a name, the circumgalactic medium, and it is so tenuous, so close to empty, that for a long time we had almost no way to measure it. You cannot photograph it. It gives off almost no light of its own. To find its edge, astronomers had to borrow light from something far behind it and watch what the gas did to that light on its way through. The borrowed light comes from quasars, the blazing cores of distant galaxies, each one powered by a giant black hole and shining across billions of light-years. Pick a quasar that sits far beyond Andromeda, directly behind its gas halo from our point of view, and its light must pass through that halo to reach us. As it crosses the gas, atoms in the halo absorb very specific wavelengths, biting narrow dark gaps into the quasar's spectrum, and each gap is a fingerprint telling you exactly what gas is there and how fast it moves. One quasar gives you one needle of light threaded through the curtain, one thin core sample of the halo. A team led by Nicholas Lehner did this with 43 quasars at once, 43 needles piercing the halo of Andromeda at 43 different points, and out of those punctures they built a map. What the map showed stopped them short. Andromeda's gas halo does not end anywhere near its stars. It reaches out about 1 1/3 million light-years from the galaxy, and in some directions closer to 2 million, a vast tenuous envelope of plasma far larger than the disk and the stellar halo combined. Andromeda sits about 2.5 million light-years from us. Its gas halo, then, reaches roughly halfway across the entire gulf between Andromeda and the Milky Way. Now hold that beside what we found in the last part, our own stars reaching 1 million light-years out toward Andromeda, our own gas halo presumably reaching farther still. If Andromeda's gas comes halfway to us and our gas goes halfway to Andromeda, then the two halos are not separated by a comfortable emptiness. They are already meeting somewhere in the middle. The astronomers said it plainly that Andromeda's halo is already bumping into the halo of the Milky Way. The two great galaxies of our neighborhood, the two we always draw as separate islands with a vast dark sea between them, are already touching, quietly, through their outermost gas, right now, tonight. There is a hard irony buried in how we learned this, and it matters for our whole question. We could map Andromeda's gas halo in this kind of detail precisely because Andromeda is outside us, spread across the sky where distant quasars can shine through it from behind. Our own halo, the Milky Way's, we cannot map this way at all because we are sitting inside it and there is no vantage point from which a quasar's light can pass cleanly through the whole of our gas on its way to our eye. The one galaxy whose gas halo we cannot measure by this method is the very galaxy we live in. So we do the next best thing. We measure our twin, and we reason that a galaxy so much like ours must be wrapped in a halo much like ours, and if it is, then ours reaches out just as far, and the touching is real. That reasoning is careful rather than certain, and honesty requires marking the difference. We have measured Andromeda's halo directly, along dozens of sight lines, and its size is solid. That our own reaches equally far, and that the two therefore overlap, rests on the assumption that our galaxy resembles its neighbor, which is reasonable but not proven. Still, everything we know says the Milky Way and Andromeda are close cousins in size and kind, and if that holds, then the empty space between them, the void we always imagined, does not exist in the way we pictured. Let that reach all the way down. When you look up and find the faint smudge of Andromeda, the single thing your naked eye can see that lies beyond our own galaxy, you are taught to think of it as far away across an enormous emptiness. And its center is far away, 2.5 million light-years of it. But the outer edges of the two galaxies may already be in contact, their gas mingling in the space between, so that there is no clean moment along that journey where you cross out of the Milky Way and into the void, and later cross out of the void and into Andromeda. The gap we imagined has been quietly closing from both sides all along. And this breaks the whole way we have been trying to find an edge. Every method in this story assumed that if you go far enough out, the galaxy's material eventually stops, and where it stops is the edge. But the material never cleanly stops. The stars thin out without ending, the gas fades without a wall, and now the gas does not even fade to nothing before it runs into the gas of the next galaxy. There is no point along the way where the stuff of the Milky Way simply quits and the stuff of the wider universe begins. So the physicists trying to define where our galaxy ends were forced to give up on drawing the edge by the matter at all. If you cannot find the boundary by asking where the stars or gas stop, because they never quite do, you need an edge defined by something other than the presence of stuff. You need a line drawn not by where the matter sits, but by how things move, by what still falls inward toward the galaxy, and what has been caught instead by the outward stretching of the universe. If the matter never marks a clean ending, what else could possibly mark where one galaxy stops and everything beyond it begins? If the matter never cleanly stops, then stop trying to find the edge by the matter. This is the move the physicists finally made. Instead of asking where the last star or the last wisp of gas sits, they asked a different question entirely, one about motion rather than presence. For any point around the galaxy, they asked which way things are moving there, whether the material at that spot is falling inward, pulled back toward the Milky Way, or being carried outward, swept away by the expansion of the universe itself. The edge, in this way of thinking, is the surface where those two fates change places. To see it, you have to picture the whole region around the galaxy as a slow, endless rain of matter falling inward. Over billions of years, shell after shell of material has been drawn toward the Milky Way by its gravity, and each shell falls in, sweeps past the center, and swings out the far side to some highest point before gravity turns it around and pulls it back. Think of a ball rolled down into a deep bowl. It rushes down one side, across the bottom, and up the other side to a peak, then rolls back, again and again. The matter falling into the galaxy does the same, and the farthest point it reaches on that first great swing outward is a special place, because material piles up there, hanging for a moment at the top of its arc before falling back in. That pile-up forms a real, physical shell around the galaxy, a place where the density of matter jumps because so much of it is turning around at once. Astronomers call it the splashback radius, named for exactly what it describes, the outer edge of the region where matter has fallen in and splashed back out. Inside that shell live all the things that have been drawn into the galaxy and swung through it at least once, bound to it, orbiting it, belonging to it. Outside it lies material that has never yet fallen in, or that the stretching of the universe is carrying away for good. The splashback radius is a boundary drawn not by where the stuff is, but by whether the galaxy's gravity has ever caught it, and it marks the true dynamical size of the thing. There is an older, more familiar version of this kind of edge, one the simulators had used for decades, called the virial radius. It marks the region where the matter has settled into a kind of balance, where it has orbited long enough that its motion and the pull of gravity have reached a stable equilibrium, neither collapsing further inward nor flying apart. Inside the virial radius, the galaxy is a settled, self-governing system. It is a cleaner line to draw in a computer model, defined by how dense the region is compared to the average of the universe, and for a galaxy like ours, it sits somewhere near 300,000 light-years out from the center. The splashback shell lies farther still, out beyond the settled zone, marking the ragged outermost limit of everything the galaxy has ever pulled in. In 2020, an astronomer named Alice Deason and her colleagues took these ideas and pinned an actual number on the Milky Way. Using computer models of galaxies like ours and the real motions of the small dwarf galaxies scattered around us, they looked for the place where the velocities of those dwarfs suddenly drop, the telltale signature of matter turning around at the edge of its fall. They found that boundary at about 950,000 light-years from the center, which makes the galaxy nearly 2 million light-years across, more than 15 times the width of the luminous disk we started this whole story with. That number, the one that opened our first hour, comes from this, from tracing not the light of the galaxy but the reach of its gravity, the farthest place it can still turn infalling matter around. And here the neighbor comes back to complicate everything, exactly as it did with the gas. The splashback edge, the cleanest and most natural boundary in an isolated galaxy, becomes blurry and ill-defined when another large galaxy sits close enough that their halos overlap. The Milky Way is not isolated. Andromeda looms right there, its outer reaches already mingling with ours, and in that shared region the simple picture of matter falling neatly toward one center breaks down because there are two centers pulling at once. So Deason's team found they could not cleanly use the outermost splashback shell for our galaxy, and fell back on the inner, settled edge, the boundary of the material that has orbited and balanced as the more reliable line to draw. Even the motion-based edge, the one designed to sidestep the problem of matter that never stops, gets smeared by the presence of the galaxy next door. What I keep close about this whole idea is how much it changes the meaning of belonging one more time. A clump of matter a million light-years out belongs to the Milky Way, not because of where it sits and not because of what it is made of, but because of which way it is falling. If our galaxy's gravity has caught it and pulled it into the great slow orbit, it is ours. If instead the expansion of the universe has taken hold and is carrying it away into the widening dark, never to return, it is not ours and never will be. The edge is the knife-thin surface between those two destinies, between the matter the galaxy reels back in and the matter the universe pulls away forever. This is the most honest edge we have found, and it is the strangest. It is not a wall, not a shell of stars, not a place where anything you could see comes to a stop. It is a balance point in an ongoing struggle, gravity pulling inward against a universe stretching outward, and the galaxy ends precisely where gravity loses that contest. Draw that surface, and you have drawn the truest boundary of the Milky Way, the line past which the galaxy can no longer hold on. But a balance point is not a fixed thing. It depends on the forces on both sides staying as they are, and the forces are not staying as they are. The largest object anywhere near us, Andromeda, is not being carried away by the expanding universe at all. It is falling toward us, closing the gap between the two galaxies a little more with every passing year, on a course that will end with the two of them becoming one. So this edge, the truest one, the one drawn by what falls inward and what flows away, has a problem built into it. What happens to the boundary of the Milky Way when the biggest thing beyond that boundary is coming home? Almost every galaxy in the universe is fleeing from us, carried away by the expansion of space, their light stretched and reddened as they go. Andromeda is the great exception. Back in 1912, an astronomer named Vesto Slipher measured its light and found it shifted the other way, toward the blue, the signature of something coming closer rather than moving away. Of all the large galaxies in the sky, our nearest major neighbor is falling toward us, and it has been falling toward us the whole time we have been arguing about where our own galaxy ends. The reason Andromeda approaches while the rest of the universe recedes is the same physics that drew this whole story. Out at great distances, the stretching of space wins, and galaxies are swept apart faster than gravity can hold them. But Andromeda is close, close enough that the mutual pull between the two galaxies overpowers the expansion, and instead of being carried off, the two of them are bound to each other, falling together across the gap. Andromeda sits inside the Milky Way's reach, and the Milky Way sits inside Andromeda's, and each is slowly reeling the other in. It is coming fast, about 110 kilometers every second, roughly 250,000 miles an hour. And yet the space it has to cross is so enormous that even at that ferocious speed the journey takes billions of years, which tells you, more plainly than any number, just how empty the gulf between two galaxies really is. A thing moving 250,000 miles an hour, and it still needs billions of years to arrive. The emptiness between galaxies is not the kind of distance the human mind was built to feel. For a long time, we thought we knew exactly how this ended. In 2012, astronomers used careful measurements to predict that in about 4.5 billion years, the Milky Way and Andromeda would slam together, tear each other's spiral arms apart, and slowly settle into a single vast elliptical galaxy a featureless ball of stars that people started calling Milky. In that future, the question we have spent all this time on simply dissolves. When the two galaxies merge, there is no longer a Milky Way edge and an Andromeda edge. No boundary between them at all, just one new object with the old borders erased. The edge of our galaxy, in that story, does not get measured. It gets abolished. Then, very recently, that certain future came apart. In 2025, a team led by Til Sawala, working with the same Durham astronomer who had measured the edge of our galaxy, ran 100,000 simulations of the coming encounter using the best data from Gaia and from Hubble. This time, they did something the earlier prediction had not fully done. They included the pull of the Large Magellanic Cloud, and they honestly folded in all the uncertainty in every measurement. The confident collision melted into a coin flip. Their simulations found only about a 50% chance that the two galaxies merge at all within the next 10 billion years, and only a 2% chance in the next 5, with many scenarios showing the two galaxies sailing past each other and going on, mostly apart, for ages more. The thing that overturned a century of certainty was the small companion galaxy we met earlier, the Large Magellanic Cloud, tugging the Milky Way gently off to one side, just enough to change whether we strike Andromeda or slip past it. A minor satellite, nudging the whole galaxy, and the difference between a cosmic collision and a near miss hangs on that nudge. The fate we had written in every textbook, the death and rebirth of our galaxy as Milky, turned into something we genuinely do not know. And this is where the whole story we have been following folds back on itself. For 100 years, every time we said the edge of the Milky Way is here, the edge moved because we kept learning to see more. Now we have done the same thing to the galaxy's future. We said, with confidence, that our galaxy would end by merging with Andromeda, and then better data turned that ending into a maybe. The answer to where the galaxy ends keeps changing, and so, it turns out, does the answer to how the galaxy ends. Both are still open. Both are still moving under us. So the truest edge we found, the dynamical boundary drawn by what falls inward and what flows away, has a deeper strangeness than a mere expiration date. It is provisional in every direction. It is drawn against a neighbor whose arrival is now a coin flip inside a system still being computed, describing not a fixed object but a moment in an unfinished process. The edge of the Milky Way is not a wall you could ever reach, and not even a stable frontier that simply waits to be crossed one day. It is a line in a story that is still being written, and the next chapter, the one where two galaxies either merge or pass, has not been decided even by the universe itself. There is a quiet humility in the people doing this work that I keep close. The same astronomer who drew the outer edge of our galaxy, who put the number near 2 million light-years across, is also an author on the paper saying we might avoid the merger entirely and keep our galaxy whole. She measured the boundary, and then helped show that the boundary's future is uncertain, and reported both with the same steadiness. That is what it looks like to hold a question and honestly, to state the best answer you have and mark, just as clearly, everything about it that could still change. Step back from all of it, from Herschel counting stars to a coin flip over Milky, and a suspicion starts to form. Every edge in this story has been a snapshot of something in motion, a line drawn across a process that never actually holds still. The disk fades, the gas warps, the dark halo reaches out to touch a neighbor, the boundary itself waits on a collision that may never come. Maybe the trouble was never that our galaxy is unusually hard to measure. Maybe the trouble is the word edge and our stubborn need for one, when nature almost never draws the clean lines we keep demanding of it. Does anything in the universe truly have the kind of edge we have been searching for all this time? Step away from the galaxy for a moment and look at something close, something under your feet, and you find the same problem waiting there. Ask where the land ends and the sea begins, and it sounds like the easiest question in the world until you actually go stand on a beach and watch. The waterline moves with every wave, retreats and advances with the tides, shifts a little each hour, so that the edge of a continent is not a line at all but a smeared, breathing zone that never holds one position for 2 minutes together. The coastline you see drawn so crisply on a map is a convenient fiction, chosen from among an endless number of possible lines, none of them the true and final one. Look up instead of down, and the sky does the same thing. Ask where Earth's atmosphere ends and outer space begins, and there is no wall, no ceiling, no moment where the air simply stops. The atmosphere just thins, fading out gradually with height, each mile holding less air than the mile below, trailing off into near nothing without ever reaching a clean zero. So we invented a line. By international agreement, space is said to begin at an altitude of about 100 kilometers, roughly 62 miles, a boundary called the Kármán line, and it is a genuinely useful number for deciding who counts as an astronaut and where a country's airspace ends. But nature did not put it there. We did, for our own convenience, and different organizations even draw it at different heights, because it was always a choice rather than a discovery. Now go all the way out to the edge of the solar system and watch what happened when a real spacecraft actually tried to cross it. The sun blows a constant wind of charged particles out in every direction, and that wind carves a great bubble in the thin gas between the stars. The surface of that bubble, where the sun's outward pressure finally gives way to the pressure of interstellar space, is called the heliopause, and it is about as close to a physical edge of the solar system as anything gets. In 1977, we launched Voyager 1, and after 35 years of flight, it reached that boundary, some 11 billion miles from the sun, more than 100 times farther out than Earth. And here is the part that should change how you think about edges forever. When Voyager 1 crossed the heliopause, on the 25th of August, 2012, no one on Earth could tell that it had. The instrument that would have measured the change directly had broken years earlier. The magnetic field, which everyone expected would swing to a new direction at the boundary, stubbornly refused to change the way the theories predicted, and the scientists fell into a long argument about whether the crossing had really happened at all. It took a lucky burst of solar activity months later, in the spring of 2013, to set the surrounding plasma ringing in a way the spacecraft could measure, and only then, by reading that ringing, could the team confirm what had happened? More than a year after Voyager actually left, the scientists finally agreed that it had. The most distant object human hands have ever built crossed the outer edge of our own solar system, and the people who launched it needed over a year of debate to decide the crossing had occurred. Even a real physical boundary did not announce itself. It had to be inferred, argued over, reconstructed from indirect clues, exactly like every edge of the galaxy we have chased in this story. And even now, the answer depends entirely on what you mean. Voyager 1 is in interstellar space, out past the sun's wind, and that is true. Voyager 1 is also still inside the solar system, because the sun's gravity holds a vast shell of icy worlds, the Oort cloud, reaching far, far beyond the heliopause, and on that definition the spacecraft will not leave the solar system for another 30,000 years. Both statements are correct at once. The solar system, like the galaxy, does not have one edge. It has the edge of the wind and the edge of the gravity, and they disagree by a factor of hundreds, and choosing between them is choosing a definition, not finding a fact. So the trouble was never that the Milky Way is unusually slippery. Coastlines, atmospheres, solar systems, galaxies, none of them come with the single clean line we keep asking for, because sharp edges are mostly something minds impose on a world that prefers to fade, to blur, to trail off by degrees. The question we started with, how far is the edge of the Milky Way, quietly assumed there was one edge to find. The deeper answer is that the honest question was always the edge of what, measured how, and how sure are we, and that is not a failure of the science. That is the science telling the truth about a universe that does not partition itself neatly for our convenience. There is something I find quietly admirable in how the best of this work is done. The same astronomer who measured the outer edge of our galaxy and gave us that number near 2 million light-years is the one who also showed the galaxy's future, is a coin flip, and reported both with the same plain honesty. She drew the line and marked its uncertainty and stood ready to redraw it when the next data arrive. That is the difference between a scientific edge and the edges on an old map. Both are drawn by human hands, but the scientific one comes with its own error bars stapled to it, a built-in confession of exactly how provisional it is and a standing promise to move it the moment the world insists. Which leaves one last strangeness, and it points not outward at the galaxy but inward at us. If nature so rarely draws these lines, if the coastline and the Kármán line and the heliopause and the galaxy's edge are all, in the end, boundaries we impose rather than boundaries we find, then the hunger for a clean edge is not coming from the universe. It is coming from somewhere inside the one doing the asking. We insist on edges the world never provided. We feel their absence as a discomfort. We keep demanding a line where there is only a fading. Why does the human mind need an edge so badly that the universe's refusal to supply one feels almost like a problem to be solved? The reason we demand an edge the universe never drew is that the human mind is, at its core, a machine for drawing edges. The world arrives at your senses as a smooth, unbroken flood, one thing shading into the next with no gaps anywhere, and a mind that took it in that way, raw and continuous, could never act on it. So the mind does something clever and a little violent. It slices the continuous world into pieces, sorts those pieces into categories, and draws sharp lines where nature left only gradual change, because a world cut into named, bounded things is a world you can think about and move through. Every edge you perceive is partly a report about the world and partly a decision made inside your own head. You can catch your mind in the act with a rainbow. The band of colors arching across the sky is a perfectly smooth spectrum, light sliding continuously from long wavelengths to short, with no dividing lines anywhere along it. Nothing in the physics marks where red stops and orange begins. And yet you see distinct stripes, a handful of separate colors laid side by side, because your mind takes that seamless gradient and chops it into bands. Different languages even chop it differently, some naming fewer colors, some drawing the boundaries at different places along the same unbroken light, which tells you that the stripes were never fully out there in the sky. Part of the rainbow's structure was assembled inside the people looking at it. This same instinct, pressed against the unknown, built the old maps. For most of history, cartographers worked with a small island of charted land surrounded by vastness they had never seen, and they could not bear to leave the edges simply blank. They wrote terra incognita across the unknown regions, unknown land, and around the margins they drew sea serpents and monsters and beasts, populating the places their knowledge ran out with invented creatures. One surviving globe, made around 5 centuries ago, actually carries the words, "Here are dragons near the far coast of Asia," the single documented example of a phrase that legend has since attached to all such maps. The impulse behind it was real, even where the phrase was rare. Faced with the boundary of what they knew, mapmakers would rather draw a definite edge and fill the beyond with monsters than tolerate an honest, featureless blank. There is something in that I find deeply human rather than foolish. The cartographer painting a dragon at the rim of the world was not simply being superstitious. He was marking, as best he could, the place where his knowledge stopped, and to anyone using that map, knowing where the edge of the known lay mattered almost as much as the knowledge itself. The dragon was a warning and a confession at once, a way of saying, "We have reached the limit of what we understand, and past this line we are only guessing." The need to bound the unknown, to give it an edge even if the edge is wrong, runs very deep in us, older than any telescope. So it is fair to turn the question on ourselves and ask whether the modern map of the galaxy is really so different. We too have a small island of the charted surrounded by vastness. The most precise map of the Milky Way ever made, built from Gaia's decade of measurements, contains close to 2 billion stars, and that magnificent catalog amounts to barely 1 star in 100 of all the stars our galaxy holds. Our finest map is more than 99% empty, a thin scattering of the known across an enormous dark we have not charted at all. And across that mostly blank map, we have confidently drawn an edge, a boundary near 2 million light-years out, exactly where the old cartographers drew their coastlines and their dragons, at the ragged limit of what we can reach. But there is one difference, and everything turns on it. When the old mapmaker drew his edge, he drew it as a solid fact, a firm line with a monster to guard it, and gave you no way to know how much of it was real and how much was fear filling a void. When the modern astronomer draws the edge of the galaxy, she staples a number to it that the cartographer never had. The uncertainty, the plus or minus, the honest admission of how far the true line might sit from the one she has drawn. The same astronomer who placed our galaxy's edge near 2 million light-years also told us its future is a coin flip and reported both with the same steady voice. The dragon and the error bar are cousins, both marking the limit of knowledge. But only the error bar comes with a promise to move the moment better data arrive. That is the quiet dignity of how we now draw the unknown. We still cannot help ourselves, still reach for an edge, still feel the blank as something that needs a line across it, because we are the same boundary-drawing creatures we always were. But we have learned to draw the line in pencil and to write beside it, in plain view, exactly how unsure of it we are. The map still has its terra incognita. We have simply stopped pretending the dragons are real and started labeling them as the guesses they always were. And this brings the whole journey home to where you are lying. You are resting tonight inside a room, and the room has walls, real ones, a clear edge between inside and out, and that boundary is part of what lets you rest. The room sits inside a house, the house inside a city, the city on a world with a curved and definite horizon, and every one of those edges gives the mind something to hold. But the room and the house and the world all sit inside a galaxy that has no wall anywhere, no true edge, only a slow fading and a boundary we drew ourselves and marked as uncertain. The same mind that needs the walls of the room in order to sleep is the mind that went looking for 200 years, for a wall around the galaxy that was never there to find. Which leaves the map where every map in this story has been left, unfinished, mostly blank, with an edge drawn lightly at the limit of our reach and flagged as provisional. And right now, tonight, new machines are being built and turned toward that blank. Instruments sharper than Gaia, designed to fill in the dark we have not charted and to test the edge we have only sketched. If the whole history teaches anything, it is that the next instrument does not confirm the old edge. It moves it. So which of the confident numbers we have spoken tonight is already, quietly, wrong, waiting for the next machine to catch it? The machine that will move the edge again is already open, already staring at the sky, and it began sending back its first images only last year. It stands on a mountaintop in Chile called Cerro Pachón, an 8-meter telescope carrying the largest digital camera ever built, a device the size of a small car holding more than 3,000 million pixels. In a single shot, it captures a patch of sky about 45 times the size of the full moon, and it moves fast enough to photograph the entire southern sky every 3 or 4 nights, over and over, for 10 straight years. No telescope before it has ever swept the whole sky this deep, this often, for this long. There is a fitting name on that observatory. It is called the Vera C. Rubin Observatory, after the astronomer we met earlier, the one who measured the spinning of galaxies and found them turning far too fast, the one whose stubborn rotation curves first forced us to accept that most of every galaxy is invisible. She spent years being doubted, building her case one galaxy at a time, and now, the largest camera humanity has ever made carries her name and points at the same darkness she uncovered. The instrument that revealed the pull of dark matter has become the instrument built to map its shape. For the edge of our galaxy, this machine changes what we can reach. Gaia measured 2 billion stars with breathtaking precision, but it could only catch stars bright enough to register, and the faint ancient stars scattered through the outermost halo mostly slipped beneath its notice. The Rubin telescope sees far deeper into the dark, faint enough to pick out the dim pulsing stars and aging giants strewn across the very outer reaches, out where the halo thins toward nothing. The 200 stars that trace the halo to 1,000,000 light-years were found almost by accident, in data meant for something else. This observatory will hunt them on purpose, sweeping the outer halo for its faintest members, filling in the sparse edge we could only sketch before. But its deepest power for our question is a way of weighing the invisible directly, by watching what it does to light. Mass bends the path of light. A concentration of matter, even matter that gives off nothing, warps the space around it, and light from distant galaxies passing nearby gets subtly bent, its image stretched and distorted on the way to us. Any single galaxy's distortion is far too slight to notice, a shape nudged by a hair. But average the shapes of billions of distant galaxies across the sky, and the tiny systematic warping betrays exactly where the unseen mass sits and how much of it there is. Picture reading a page of text through a thick, flawless sheet of glass. You cannot see the glass itself, it is perfectly clear, but you can see how it bends and smears the letters behind it, and from that warping you could work out the shape of the lens without ever seeing the lens. Dark matter is that invisible glass, the distant galaxies are the text, and the gentle distortion of their light is how we read the shape of the thing we cannot see. With billions of galaxies as its text, the Rubin telescope will map the dark matter across the sky, weighing halos by their gravity's grip on light, rather than by the scattered handful of stars that happen to orbit through them. So the edge of the Milky Way is about to be measured yet again, more deeply than ever, by fainter stars and by the bending of distant light. And it would be a mistake to think this is the last word. It is only the next one. Every instrument in this story moved the edge, and none of them confirmed the number they inherited. Herschel's star counts gave way to Shapley's clusters, which gave way to the radio maps of the gas, which gave way to the rotation curves and the dark halo, which gave way to Gaia's billion stars, and now to this. Each was the best answer of its moment, and each was quietly overturned by the machine that came after. That is the truest shape of what we have been watching, and I keep it close because it is easy to forget. The size of the Milky Way is not a fact we are slowly approaching, a fixed truth we will one day reach and hold. It is a living estimate, a best current reading, carried forward from one generation of instruments to the next, always marked with how far it might still be wrong. The number near 2 million light-years that we spoke of at the start of tonight is where the reading stands now, and it stands there honestly, with its uncertainty attached, waiting for the mountain in Chile to nudge it once more. And notice the one thing that has not changed across all of it, from a homemade telescope in an English garden to the largest camera ever built. Every one of these instruments, however vast, however precise, sits inside the galaxy it is trying to measure. The Rubin telescope, for all its power, still stares outward from within the disk, still gathers only the light that reaches its mountain, still works from the inside of the very thing it is mapping. We have never once stepped outside to look back, and we never will. The whole enterprise, 200 years of it, has been the work of a creature trapped inside its own home, reasoning out the shape of the walls from the light that leaks in. There is a way to feel that trap tonight, without any instrument at all, using nothing but your own eyes and a dark enough sky. The band of the Milky Way overhead is the disk of our galaxy seen edge-on from within, and depending on which way you face, you are looking either in toward the crowded center or out toward the thinning edge. The light landing in your eye from those faint outer stretches left its stars tens of thousands of years ago, before cities, before writing, and it has been crossing the dark the whole time to arrive on this particular night. When you look up at that pale river of light, which direction is the edge we have chased all this time? And how old is the light you are actually seeing? Tonight, if you can get to a dark enough sky, you can look up and see the whole of this 200-year argument laid out overhead as a band of pale light. That soft river arching across the sky is the disk of our galaxy seen edge-on, from a seat inside it, and depending on which way you turn, you are looking either in toward the center or out toward the edge we have chased all this time. The two directions look nothing alike, and the difference between them is the whole structure of the galaxy, written where anyone can read it. Face the brightest, broadest part of the band, the direction of the constellation Sagittarius, and you are looking in toward the heart of the Milky Way. The light there is thick and luminous because your line of sight plows through tens of thousands of light-years of densely packed stars, layer upon layer of them piled toward the crowded center. Now turn to the opposite point in the sky, out toward the border of Taurus and Auriga, and the band grows thin and faint, easy to miss. That direction is called the antecenter, and it is you looking outward, along the radius, toward the rim of the disk, through a far thinner scattering of stars that runs out quickly into the dark beyond the edge. The brightness of the band, then, is a direct readout of how much galaxy lies along your gaze. Bright toward the center where the stars pile deep, dim toward the edge where they thin and end. With nothing but your eyes, no telescope at all, you are measuring the shape of the galaxy the same way Herschel tried to, by how the starlight thickens in one direction and fades in another. When you glance at the faint winter Milky Way toward Auriga and find it disappointing, thin, and washed out, you are looking straight out toward the edge, and its faintness is the edge announcing itself as plainly as it ever will. And the dust is up there too, still doing exactly what it did to every early map. Even facing the bright center, you are not seeing the true core of the galaxy, because the same haze we tracked earlier hangs between you and it, blocking the visible light and hiding the heart entirely. Those dark lanes and rifts that split the bright band, the ragged black channels running down its length, are that very dust, the invisible fog that fooled Herschel into a galaxy too small and centered on himself. The whole story is legible overhead on a clear night, the density of the stars and the dust that obscured them, the center we cannot see and the edge that fades into nothing. There is something about the age of that light I keep close. When you look out toward the rim, toward the outer reaches of the disk in the direction of the anticenter, the light landing in your eye left those distant stars tens of thousands of years ago. It set out across the galaxy before anyone had written a single word, before farming, before the last ice age loosened its grip, and it has been crossing the dark this entire time to end its journey, tonight on the back of your eye. Some of the oldest light you will ever personally receive is not from a telescope or a distant quasar. It is the ordinary glow of our own galaxy's far edge, finishing a journey older than human memory against the retina of someone lying still in the dark. And here I want to say something about how this edge was actually found, because it was never the work of a few lonely geniuses. Herschel counted his stars with his sister Caroline beside him in the cold, catching every number as he called it down. The whole ladder of distances that let us measure the galaxy rests on the pulsing stars first understood by Henrietta Leavitt, whose law turned a rhythm into a ruler. The habit of watching those variable stars, of tracking their steady brightening and dimming night after night, has long included ordinary amateur observers, people with modest telescopes and patient eyes, who logged the pulses that the professionals later leaned on. The farthest stars we know of in our galaxy were pulled by a graduate student out of data gathered for something else entirely. The edge of the Milky Way was moved outward, across 2 centuries, by a long chain of attention, much of it uncredited, some of it done by hand in the dark for the love of it. No single person ever measured the galaxy. Thousands of people did, each adding a small correction, each handing the question forward a little more honest than they received it. And tonight, simply by looking up and understanding what you are seeing, by knowing that the bright side is the center, and the faint side is the rim, and the dark lanes are the dust, you are standing exactly where every one of them stood. Inside the galaxy, looking out, reading its shape from the light that reaches you. That is the strange gift of this whole question. It was never something happening far away, in journals and observatories, separate from you. The disk whose edge we cannot pin down is the same disk arching over your roof right now. The dust that shrank the early maps is the same dust darkening the band tonight. The light from the edge is landing on you, and the mind that cannot help reaching for a boundary the galaxy never drew is the same mind lying here, looking up, wondering where it all ends. And that ancient light, older than writing, finishes its long crossing at a very particular place. It ends on the surface of your eye, at the boundary between the outside world and you. Which is a strange place to leave this, because we have spent the whole night showing that the galaxy has no clean edge, that its boundary is a fading and a choice rather than a wall, And now the galaxy's oldest light arrives at what feels like the one obvious edge left in the universe, the edge of your own body. But press on that a little. The light stops at your eye, and your eye is part of you, and you feel yourself to be a bounded, separate thing, lying in a bounded, separate bed. Where, exactly, does your body end? Your body does not end at your skin. It feels like it does. The skin seems like a clear wall, a closed surface with you on the inside and the world on the outside, one obvious boundary in a night full of things that would not hold still. But look closely at what your skin is actually doing, right now, as you lie here, and the wall turns out to be a busy, open border, with traffic crossing it in both directions every single second. Start with heat. Your body is running warm, its surface a few degrees hotter than the air of the room, and because of that difference, it is pouring heat outward continuously, somewhere around 100 watts of it, about what an old incandescent light bulb gives off. That warmth does not simply vanish. It heats the thin layer of air touching your skin, and that warmed air, being lighter than the cooler air around it, rises so that a slow, steady current flows upward off your body, a soft, invisible column lifting from you toward the ceiling. It carries your heat, and it carries the tiny flakes of skin you are always shedding, up and out into the room. You are not sealed inside your outline. You are gently rising off yourself into the air above the bed. And it is not only heat that crosses. Your skin releases water vapor without pause, a thin, invisible breath from the whole surface of you. With every breath, your lungs pull the room's air deep inside and send it back out again, warmed and changed, trading molecules with the space around you thousands of times a night. You shed cells, you take in air, you give off warmth and moisture, and atom by atom the material that makes you is constantly being exchanged with the world, so that the you of a year from now will be built partly from air and water and food that tonight is still out there, not yet you. The boundary of your body is not a wall holding a fixed thing inside. It is a shoreline where a slow, endless tide comes in and goes out. Then there is the question of what even counts as you. Living on your skin and inside your gut, right now, are trillions of bacteria and other tiny organisms, a whole teeming population that is not, in the usual sense, you at all. For decades, scientists repeated a striking figure, that these microbes outnumber your own cells 10 to 1, that a human being is 90% bacteria wearing a thin coat of human. Then, not long ago, researchers actually went back and checked the arithmetic and found the old number wrong. The real ratio is close to 1 to 1, roughly 38 trillion microbial cells against about 30 trillion of your own, near enough to even that a single trip to the bathroom can tip the balance back in your favor for a few hours. Even the count of how much of you is you was a confident number that kept changing the moment someone measured it carefully, the same way every edge in this story has. You are, by cell count, about half yourself and half a garden of other living things, and there is no clean line on your skin dividing the one from the other. Now here is the part I want to be careful with, because it is easy to hear all this as a pretty comparison and miss what is actually true. This is not a metaphor for the galaxy. It is the same problem, the very same one running on your bed tonight. Remember how the truest edge of the Milky Way turned out to be drawn not by where the matter sat, but by exchange, by what falls inward and what flows away, a boundary defined by motion across it rather than by a wall. Your body's edge is exactly that kind of boundary. It is not a surface where you stop and the world starts. It is a zone of exchange, defined by what crosses it, heat and water and air and cells and atoms passing through in both directions, never still. So ask the question we have asked all night, the only honest one, and ask it of yourself. Where do you end? At the skin, the surface you can touch, or at the edge of the warm plume rising off you, which is still unmistakably yours, still your heat, still your shed cells, drifting a foot above your body. Or out at the boundary of the air your breath has reached and changed, or somewhere among the trillions of small lives that share your body and help run it, that are half of you by number and not human at all. Each of those is a real answer, and they sit at different distances from your center, and they do not agree, exactly as the edge of the light and the edge of the gas and the edge of the mass did not agree for the galaxy. The edge of what measured how? The same question on the same night about you. And I find this settling rather than frightening, once it stops being strange. You were never a sealed thing set down in a room, holding yourself apart from everything else. You are a pattern the world keeps flowing through, a slow, steady exchange of heat and breath and matter that has been going on since before you can remember and will go on without any effort from you tonight. The warmth leaving your skin, the air moving in and out, the quiet trade of atoms with the room, none of it needs you to manage it. It simply happens, the way the galaxy holds its outer stars without trying, the way the tide comes in without being told. So there is no wall around the galaxy, and no wall around you, only fadings, only boundaries drawn by what passes through them. The 200 years of looking for the edge of the Milky Way and the simple question of where your own body ends arrive at the same quiet answer. There is no line. There is only exchange and gradual fading, and the choice of where to say the edge lies, which leaves almost nothing left to hold on to as the night closes. The galaxy has no edge to reach. The body has no wall to defend. The self blurs gently into the room and the air and the small lives it carries. So when everything you thought had a boundary turns out to be a fading instead, what is there left, tonight, that is yours to keep? Maybe nothing is left to hold on to tonight. And maybe that is exactly the right place to end. Because after all of it, after 200 years of measuring and arguing and moving the line, one quiet fact sits underneath everything we found, and it is the fact worth carrying into sleep. The galaxy never changed. Through every one of those shifts, when the edge jumped from 100,000 light-years to 1,000,000, from the disk of stars to the halo of gas to the vast dark sphere of unseen mass, the Milky Way itself did nothing. It did not grow. It did not stretch to stay ahead of us. It has been exactly this size, exactly this shape, turning slowly with the sun tucked 2/3 of the way out, for longer than there have been eyes on this planet to wonder about it. Every time the answer changed, the change was never in the galaxy. It was in us, in what we could reach, in how much of what was always there we had finally learned to see. That is the real answer to the question we started with. How far is the edge of the Milky Way, and why does the answer keep changing? The answer keeps changing because we keep growing into it, because each generation hands the next a slightly larger view, and the edge moves outward not because the universe is restless, but because we are still arriving. The galaxy was patient. We were the ones in motion the whole time. And the uncertainty we are left with, that soft blur where the number could still be wrong by hundreds of thousands of light years, is not a failure. It is the most honest map anyone has ever drawn of our home. The old maps were confident, and they were wrong. A small, tidy galaxy with us at the center, sure of itself and mistaken. This map is uncertain, and it is true, drawn lightly, with its own doubt written plainly beside every line. That is not the science falling short of an answer. That is the science telling the truth about a universe that fades instead of ending, that offers gradual edges and asks us to be honest about them. So there is nothing to hold at the edge tonight, because there is no edge, only a fading, and a fading asks nothing of you. The galaxy has no wall for you to guard. Your own body has no wall either, only that same soft border of exchange, heat rising off you into the dark room, breath moving in and out, the slow, quiet trade of matter with the world that needs no effort and no attention from you at all. The thing you were reaching for all night, a final line, a fixed answer, a place where things at last stop, was never out there to be grasped. And letting go of it is not losing anything. It is setting down something you were never actually holding. Feel where you are for a moment, without trying to fix its edges. You are lying near the center of a dark halo, 1,000,000 light years wide, a structure you cannot see and were never meant to escape, and it holds you effortlessly, the way it holds every distant star at the rim. You do not have to help it. While you sleep tonight, in the 8 or so hours ahead, the sun will carry you and the whole Earth about 4 million miles along its enormous orbit around the galaxy's center, roughly 6.5 million kilometers of travel through the dark, and you will feel none of it. You will not have to steer, or hold on, or stay awake to make sure it continues. The galaxy carries you whether you grip it or release it. So you can release it. Your breath is already slowing. Your heart is easing down toward its quiet nighttime rhythm. These are not separate from everything we have talked about tonight. They are the same kind of thing, a body coming gently to rest, a system settling toward its own quiet balance, the same slow drift toward stillness that governs falling matter and cooling stars and every edge that ever softened into a fading. You are doing right now, in your own chest, the most ordinary version of what the whole universe does. Coming to rest. There is nothing left tonight that you need to understand, or measure, or hold. You followed the edge all the way out, past the last stars, past the gas, past the invisible mass, out to where it touches another galaxy and dissolves, and you found, at the end of it, that there was no wall anywhere, and that this is a kind of freedom. Nothing to defend, nothing to keep, nothing to carry into sleep except the quiet knowledge that you were never separate from any of it to begin with. Thank you for staying out here with me tonight, all the way to an edge that was never there. It has been a real comfort to think through this with you, slowly, in the dark, the two of us turning a very old question over until it softened. I am grateful you spent these hours here. There is nothing more to reach for now. The galaxy is holding you, and it will go on holding you all night without being asked. Let your breath go long and slow. Let the edges blur. Let yourself be carried. Rest now. Good night.